Section 1.5 talks about limits involving infinity. So up until now, we've sort of mentioned this idea of asymptotes before, but we haven't really gone down that rabbit trail very far, right? In fact, I haven't even talked too much about that except to say, hey, this is what's happening, let's move on. So we're going to talk about that in this section. I want you to first recall the basic graph equation of the the rational equation graph of f of x equals 1 over x. And I've drawn a portion of this before, but not all of it. So this graph of 1 over x looks something like this. Okay, does everybody remember that graph? We say that this graph has two asymptotes. One is vertical, and that's the y-axis. The other is horizontal, and on this case, it's the x-axis. So this is my vertical asymptote. And that's not a good color. Let's try again. That one is my horizontal asymptote. So the first part of what I'm going to talk about today is something you've seen before. You've seen it in an algebra class, either in high school or in college. It's talking about finding asymptotes. Now, before we talk about the finding the asymptotes, let's just make a mention about some strange things that are going on with limits. If we talk about finding the limit as x approaches 0 from the right, that's that little plus sign, means from the positive side of the graph, one could say that the limit doesn't exist. Okay? Because it's going up forever. It never stops. But sometimes we also talk about that and we say the limit is infinity, which means it goes up forever and it never stops. By saying the limit is infinity, more information is conveyed than if you simply say it doesn't exist. Because a limit cannot exist for multiple reasons. Okay? But if you actually say that it doesn't exist, but you say it in terms of it's infinity, I have more information about what the graph actually looks like, what the function's actually doing. So when we have the ability to say that the limit is infinity or doesn't exist, if it's either or one's appropriate, we're going to default to saying that the limit's infinity because it gives us more information. Okay? Now let's actually talk about finding these asymptotes. We've seen this one happen, the first one already, vertical asymptotes. So the way that we find vertical asymptotes, and this is for rational functions, is we reduce the expression to its simplest form, right? That's the factoring you guys have been doing looking for limits. So we factor as much as we can, reduce it, simplify it as much as we can. And then if we still have something in the denominator, then we set the denominator equal to 0 and we solve it. And those locations that make the reduced equation equal to 0 created asymptotes. Right? You've done this before, and we've already done this even in the last section in this class. Horizontal asymptotes are a little bit more difficult because there's different options that can happen. There are three cases that can happen with horizontal asymptotes. Now, let me pause for a moment and talk about something that notationally this is written in and remind you. Do you remember what is meant by the degree of a polynomial? Yeah, and not just power, but the highest power. Okay? So when this refers to the degree of the numerator, it means the largest exponent in the numerator. Or the degree of the denominator is the largest exponent in the denominator. So there are three cases. The first case is that the degree of the numerator is greater than the degree of the denominator. So maybe you have an x squared on top and you only have an x in the denominator. Or you have an x to the fifth on top and you have an x cubed in the denominator. Okay? So if the degree on top is larger than the degree on bottom, then we do not have a horizontal asymptote. Okay? There's just not one. Second case, if the degree of the numerator is less. So instead of having the x to the fifth on top, it was on bottom. Right? So just flip what I just said a moment ago. X cubed on top, x fifth on the bottom. X on top, x squared on the bottom. So if the degree on top is smaller than the degree on bottom, then we have a horizontal asymptote and it's y equals 0. It's going to be the x-axis. Okay? So those are the two that are easy to identify. The case that sounds really awkward, and it's not hard to do it, it just sounds awkward to write it out, is if the degrees are the same. So if we have x squared on top and x squared on bottom. or x to the fifth on top and an x to the fifth on bottom. So if that happens, what we do is we take that highest degree term and we look at the coefficients in front of them, and we use those coefficients to create a fraction, 3 over 2, or 1 over 1, whatever it is, set equal to y, and that's our horizontal asymptote. So it's a ratio of leading coefficients. It is so much easier to do than it is to write. That is the most awkward thing to write down. And I don't even think it's written the way your book did, because I probably didn't like the way the book did it, because it's just awkward to write. So let's take a look at one, and you can see where this comes into play. All right, so here's the first one. If the directions say find all horizontal and vertical asymptotes. So let's just make a comment that before we get started with this, we want to reduce. That's going to be your very first thing to do. You're not looking for anything. You're not using any of those previous rules on the previous slides, nothing. You're going to reduce if possible. Okay, the numerator now does not factor, right? Because it's got a squared and their addition. So the denominator, if it did factor, and we'll need it factored later, would be where we would have something cancel out with the numerator. Now this one's not going to factor. It's not going to reduce. It's going to factor. It's not going to reduce. I said that sound funny. I've got an x on both of them. Do you know what this factors into? Good. X minus 3 and x plus 1. If you're a little bit rusty on your factoring, you might want to go take a look back at some of the material from that in section 0 in your book. There's a chapter 0, and it's got some factoring stuff in it. This is in as factored a form as it gets, and it doesn't reduce with the numerator, right? Yeah, so we're not going to be able to reduce it. If we could reduce it, we would cancel things out and we'd use the reduced form as we moved forward. We don't have that ability. Okay, so let's do the vertical asymptotes first. All right, so vertical asymptotes. How do I find vertical asymptotes? Right, and it's very helpful for us to have it in factored form, which is why I wanted to do it regardless of if it reduced. Because the denominator is going to be equal to 0 when the factors are equal to 0. So if I set x minus 3 equal to 0 and x plus 1 equal to 0, what values do I get? X equal 3 and x equal negative 1. So my vertical asymptotes are x equals 3 and x equals negative 1. Now, asymptotes are lines, which means you cannot tell me the vertical asymptote is 3. 3 is a number. It is not a line. X equals 3 is a line. You guys with me? So when you write down the answer for this, it needs to say x equals. Otherwise, you're not writing down the equation of a line. And vertical asymptotes are vertical lines, which are in the form x equals. All right, horizontal asymptotes next. All right, so horizontal asymptote means looking and seeing what happens to the degree. So can you tell me what's happening to the degrees on this particular one? They're the same, which means it's case number 3, right? The one that I said was awkward to write. They're the same, so what do? Well, we look at the numbers in front of the highest degree terms. The number on top is a 3. What's the number on bottom?
1.
It's 1. So your horizontal asymptote is y equal 3 over 1. Or more simply put, y equal 3. That's all it is. You're just looking at the coefficients in front of the highest degree terms, if the degrees are the same. Okay, so we've done these first two things. We determined the horizontal asymptotes and the vertical asymptotes. But it says for each vertical asymptote, which we have 2, we're supposed to determine whether f of x approaches infinity or negative infinity on either side of the asymptote. Okay. So let me show you what this is asking me to do. It's asking me to find 4 limits. It's asking me to find the limit as x approaches 3 from the left of my function, the limit as x approaches 3 from the right of my function, the limit as x approaches negative 1 from the left on my function, and the limit as x approaches negative 1 from the right of my function. 4 limits I'm going to find. And I'm going to find them using a calculator. So grab your calculator out and plug this equation into your calculator. Graph it. All right, so I'm just going to go in order of how I wrote them, which means the first value I'm going to be looking at is over here at 3, and then I'll look at the -1 one. So if I'm going at the x value of -3 and I'm supposed to be approaching it from the left side of the -3 is over here, correct? Which means the graph is doing this. So what is happening to my limit value? That one's negative infinity, exactly. So this one would be negative infinity. Now if I'm approaching the x value of 3 from the right, that means slightly bigger values. So I'm on the right-hand side and I'm moving towards x equals 3. What's happening on that one? That would be positive infinity. Now, if this question asked us, this answers the question you had from before, is am I never going to use does not exist again? If this particular question asked us about at x equals 3, what is the limit? That would be does not exist. Because from one side it's infinity and the other side it's negative infinity. So the limit at x equals 3 does not exist. All right, so let's do the other side. This is supposed to be at x equal -1. So at x...
If it just didn't have the plus or minus?
Yes. Yes. Now the directions on this one actually told us to do it on either side of the asymptote, right? So that's why we're doing the one-sided limits. But yes, if your limit still said, what is the limit as x approaches 3, that would be does not exist. Because I still have, they're different from each side. All right, at -1 from the left, whoops, that would be over here. What's going on?
Infinity.
That's infinity. And how about -1 from the right? That one's negative infinity.
Okay, can I ask?
Yeah, Tammy first.
How are you like choosing between the two different graphs?
Okay, so this comes back to what we've done before. This plus or this minus after the number tells you.
Yeah.
Positive means to the right. So you start on the right and you get close to the value.
No, but I mean, like, I understand that. I mean, like, between those two.
Because if I'm dealing with x equal -1, the only two graphs that are nearby that, only two pieces, are this piece and this piece.
Right, but like, on one of them, you did this side, and then the other one you did
Because this side's right. Side is to the right. This is a right-left issue. This is, between these two graphs, only one of them is on the right-hand side of x equal -1. So I have to be on that piece. So I'm on this piece because it is to the right-hand side of x equal -1. And then if I'm finding the graph, the limit as it's from the left-hand side, the negative, I have to be on this piece because it's the only piece that's on the left-hand side of x equal -1. So you have to use that plus or that minus to tell you I'm on the right-hand side or I'm on the left-hand side, and you have to go from there. Did you have a question as well?
Okay. Backing out, back to the horizontal, the HA or whatever.
Yep.
I missed that. What did you said? Whenever you like circle the 3 and like put a 1 for.
This is case 3 because the degrees are the same.
Okay.
So when the degree of the numerator and the denominator are equal, then we look at the coefficient in front of those highest degree terms. So on ours, the coefficient in front of the highest degree term on top was the 3 in front of the 3x squared. And then the coefficient on the bottom in front of the x squared was the 1.
Gotcha.
So that's where the 3 and the 1
So
came
since
from.
they were both x squared.
Yes.
Okay.
Yes. All right, one other type of asymptote. These are called slant asymptotes. So when the degree of the numerator was bigger, that was case number 1, it didn't have a horizontal asymptote, right? Yeah. Now, if the degree of the numerator is exactly 1 bigger, right, like it's x squared on top and x on bottom, x to the 5th on top and x to the 4th on bottom, it's exactly 1 bigger, then it has what's called a slant asymptote. And you can identify what the equation is of the slant asymptote by using long division. And some of you may remember something called synthetic division. Synthetic division works in some cases and not in others. So I'm going to show you the long division because it works in every case. And for what we're doing, that will keep it as the most general process that we're going to be working with. Okay? So here's an example of a function where the degree on top is 2, the degree on bottom is 1. It's exactly 1 bigger on top than on the bottom, right? So it's not going to have a horizontal asymptote. The degree on top's bigger. But it will have a slant asymptote because it's exactly 1 bigger. So I'm going to show you how, remind you how, because I know you've probably seen this before, how you use long division. Well, if you had, say for instance, 39 over 4, you'd put the 39 underneath the division sign and the 4 on the outside, right? We do the same thing with the fractional division sign this way. I'm going to put the x minus 2 on the outside, and I want the x squared plus 1 underneath. Now, for the sake of making this as simple on myself later as possible, I'm going to write it like this. I put in a 0x. I need placeholders, very much like if I had the number 309, and I just wrote the 3 and the 9, that would be unhelpful because I need that placeholder for the 0 in the tens place. I'm going to put a placeholder in a 0x in the x's place. Okay, it's just reserving that place. And then we do the same thing that we do when we look at 39 divided by 4. We ask ourselves what in the world we need to multiply x minus 2 by to get x squared. And in fact, we're just going to look at the first part, x. What do I need to multiply x by to get x squared? X. So I'm going to put an x on top here. And I'm going to multiply x times x is x squared, just what we wanted. And then I need x times negative 2, which is negative 2x. Now, when we do this over here on this problem, and I'll change it to say 309 for the moment because it'll be a little bit easier to match up with how I'm doing the other problem. We would say we need to multiply 4 by 7, and that gives me 28. What do I do with the 30 and the 28 next? I subtract, right? So I'm going to do the same thing over here. Subtracting is equivalent to changing the signs. So instead of it being positive x squared and negative 2x, I'm going to change these signs. And as I do that, sure enough, I've got x squared minus x squared, so there's no more x squareds. So I'm left with now 0x plus 2x, which is 2x. And I bring down the next term, which is the plus 1. And we do the same thing over here with this, right? 30 minus 28 is 2, and then I bring down the next value, which is the 9.
I would have never thought I would have used this again, like long division.
Oh, goodness. Yes, you will. You're going to use it more than just today, too. It's definitely here to stay for a little while longer. All right, we're almost done with this one, too. So I have the x minus 2 over here. I've got my 2x plus 1 down here. And I do the same thing. What do I have to multiply x by to get 2x? 2. So I'm going to put in here a plus 2. 2 times x is 2x. 2 times negative 2 is? Negative 4. And then I need to change my signs, because that's what subtraction is. It's changing signs. So I've got 2x minus 2x is nothing. And then 1 plus 4, which is 5. All right, so this right here is my remainder. You guys remember doing things where when you were really young is R something at the end, right? In this case, this would be 77R1. You have R at the end. The remainder is not a part of the slant asymptote. It's exactly how far away you were from actually having this evenly divide. But this piece right here is the slant asymptote. So my slant asymptote is the equation y equals x plus 2.
That remainder has no effect on the equation of the slant?
It has the effect only the effect to the extent of how close it is to the asymptote and how quickly it approaches the asymptote. But it doesn't affect what the asymptote's value is.
Right.
Yes. No effect on what the asymptote's
So it
value
doesn't
is.
affect until, like, if there was a line for that asymptote, like that is the exact equation? X
Yes.
plus 2?
This is the line. The line y equal x plus 2 is the exact line for the asymptote. I'd like for you to graph this just so you can see what it looks like for a graph to have a slant asymptote as opposed to a horizontal asymptote. So you notice on this one that I had put on the board, horizontal asymptotes over here on both ends mean that you level out flat, right? But graph this one. Take a look at what this graph looks like. I won't do it on my screen since it's not cooperating for us. But what does the graph look like when you have a slant asymptote? The original equation. We don't want the slant asymptote in there just yet. I just want you to put in f of x equals x squared plus 1 in parentheses divided by x plus 2.
Minus 2.
Oh, did I say plus 2? I was looking at the plus, I think, in my box underneath. You're right. Yes, x minus 2. Thank you.
I think it's easier to see if you graph also.
Yeah, we're going to next. But do you see how it doesn't have any of that flattening out features on the end like the last one did? It doesn't level out on the end flat. Instead, it sort of levels out slanted, right? Now, just so that you can see it like you suggested, I want you to do that. Down in y equal 2, okay, y or y sub 2, I want you to put in x plus 2. That's the slant asymptote we just found. So in y1, you have the first original graph, and in y2, you have the slant asymptote we found. And do you see how on the ends of the graph, it does the same thing? It flattens out, but it flattens out along that line instead. This is a really good thing to do, because then you can actually make sure that you didn't make a mistake in your division, right? Because if it's not approaching that slant asymptote and your image on the end, then you've got an issue with your division. Yes?
It's supposed to be x minus 2.
Nope, we had x plus 2. The x minus 2 was in the original equation. There was a denominator of x minus 2.
So when you, the second time you see x goes into 2x 2 times.
Uh-huh.
Oh, okay.
Yeah. Yeah, there was subtraction, but it was a part of the long division process. Okay.
So to get your, like, we have one asymptote, we have the, what you could call the horizontal line graph.
Mm-hmm.
How do you get the vertical one from the horizontal? Is it the opposite reciprocal? Like, if I wanted to graph that line that goes in between the vertical.
You can't graph vertical lines on your calculator. Your calculator will not graph a vertical line. It has to be in function notation, and a vertical line is not a function. So your calculator will not graph a function, graph a vertical line, I mean.
Okay.
Thanks so much.